So in the last video, I tried to give an intuitive explanation of what angular momentum and torques and the moment of inertia really mean. However, I ignored all of the sort of vectors which are actually very important here. So in this video, I'm going to rerun over these ideas, but including these vector quantities. Why do we need to do this? Well, in general, if we're talking about rotation in 3D, we're going to need to use vectors. And even when thinking in 2D, it's also useful to have these quantities. It makes things a bit more complete. So to start off with, the equation which you should have in mind when you think of the angular velocity, this omega, is of course d theta by dt. But how is this a vector quantity, and in which direction does it point? Well, what we do is we say that omega is a vector like this, in that it is equal to d theta by dt, but multiplied by a unit vector u hat. So notice that is a unit vector, so the magnitude of omega is still just given by d theta by dt, and this is why in 2 dimensions, or when you simplify things to the scalars, you still just get out that d theta by dt. Okay, but what direction does u hat point in? Well, firstly, let's imagine a particle in uniform circular motion again, and it's rotating anti-clockwise in the page like this. Okay? Well, we define a vector u hat, which lies perpendicular to that plane of rotation, such that when you look down the vector, so if you look down from this direction in, what you see is that the motion is anti-clockwise. So that's the important point in defining which direction u hat lies in. Okay? What that means is that omega also lies along u hat. It is always perpendicular and in the same direction as u hat. So also, if you look down omega, you'll see the motion happening anti-clockwise. Now what we can do is we can define some coordinate system. So the white arrow here is theta equals 0, and the yellow arrow is, of course, r, the position vector of that particle. And this is exactly how we define what theta means. It's how d theta by dt is how that angle changes with respect to time. Okay, so in the last video, you'll recall that we had omega is equal to v over r. How does this tie in with the picture of having this d theta by dt and this u hat vector? Well, the 3D generalization is this. It's omega as a vector is equal to r cross v, which is the cross product gives you back a vector, divided by the magnitude of r squared. Okay, so firstly, we can say dimensionally that this works out to the same thing. We have a magnitude of r, magnitude of v on the top, and we divide by magnitude of r squared, so this is something like a v over r. So this matches with the simple version, omega equals v over r. However, what exactly is going on with this cross product, and is this equivalent to our definition a moment ago? Well, I'm going to assure you it is, and the way to convince yourself of this is we need to think about the direction of that of the unit vector and that cross product on the top there. Well, okay, what we do is we use the right-hand rule to decide which direction that is going to point in. So we take r as along our first finger using the right-hand rule, and v, of course, is always tangential to the circle, so it's going to be like this. What that means is that your thumb tells you which direction r cross v is in, and in this picture, for example, it points out of the page. You'll also notice that the direction of v tells you whether the motion is clockwise or anti-clockwise. In this picture here, it's clearly anti-clockwise. What that means is that you are looking down the omega vector. So omega, in this case, is pointing out of the page. This fits both in with our previous picture that u hat will be pointing out of the page, and also with this picture that we have this r cross v, and when we use the right-hand rule, we see that omega is pointing out of the page. So it all ties together quite nicely. Okay, now of course we need to think about the other quantities which we had. So we had this angular momentum vector, which I said was rp in the last video. The 3D generalization of this is that L, which is a vector quantity, is equal to r cross p. Okay, so why could we simplify that in the last case? Well, you'll notice, just as we just had, in uniform circular motion, the v is always tangential to r, and so if you put in p is equal to m times v, then you just end up with r times m times v, because you have sine of 90 degrees, because that, it's tangential. And so you end up, you can sort of simplify this and just think about scalar quantities. But in general, this is the expression you should have in mind. L as a vector is equal to r cross p. Okay? What else can we, how else can we write this? Well, we can write this in much the same way as I, the moment of inertia, times omega, which is a vector. Now, I'll leave that as an exercise to you to convince yourself that those two things are the same. You can plug in mv as a vector into this top equation, and you should be able to derive this second equation here if you assume that I is equal to mr squared. The other equation, of course, which we had was the torque. Now, the torque was given by r times f in the simplified version. Here, as you may have guessed, it's going to be r cross f. So the torque is also a vector quantity. However, we also had this other definition that the torque is the rate of change of angular momentum, dl by dt. Are these two things equivalent? Again, I want you to go in and have a play with this. Try taking the time derivative d by dt of L on the top here and see if you can recover the r cross f term. If you get stuck at all, I recommend that you have a quick look at the section on cross products and what needs to be done when you're taking the cross product, sorry, the time derivative of a cross product. Okay, so we have these definitions. The torque is a vector and the angular momentum is also a vector. So returning to this picture where we had a particle rotating anti-clockwise in this way, where do the angular momentum and torque lie in this picture? Well, for the angular momentum, you can immediately see that if omega, so omega lies along this part of the plane here, so I can't quite work out exactly where to point my finger here, then L, the angular momentum, is also going to lie along that vector. It's always going to be parallel to omega. And since I is necessarily positive, it's also going to be, it's always parallel, it's never anti-parallel. Okay, but what about the torque? Well, the torque is the time derivative of L. That can be either positive or negative. However, the direction of it is quite well defined. It's going to lie, so long as I is a constant, by the way, and that's something you'll get onto much later. We're going to assume that I is constant here. But it's always going to lie parallel or anti-parallel to omega. So in this case, for example, if dl by dt is negative, or the magnitude of it, if you like, is negative, then that torque is going to act to slow down the system. What I mean by here is what I mean by this is that if you this torque is acting on dl by dt, and it is tending to make the angular momentum of the system smaller. And so in that way, you see this geometrically, it acts in the opposite direction to L and also to omega. On the other hand, if dl by dt is positive, i.e. the torque lies along the angular momentum, you're going to tend to spin the system up or add angular momentum to it, resulting in, for example, the system spinning faster. So torques and angular momentums and the angular velocity all lie along this line, which is perpendicular to the plane of motion. This is not always the case, as I was saying, and when that's not true is when I gets a little bit more complicated. But for now, it's enough to take I to be this mr squared, and you can do a lot with this. Okay. So that's all for this video, and hopefully you've got some feeling for what the angular momentum and torque and moment of inertia are in 3D. The angular momentum and torque, remember, are always vector quantities, but the moment of inertia, which plays the role of a kind of mass, in this case is just a scalar.